Sure. Hey everyone, this is Tamal, and welcome to the third video in our Road to AGI series. I'm here with me, Amritans, with whom I'm collaborating for some time. Hey Amritans, how are you doing?
I'm good. Thank you.
Sure. Yeah, so this is the third video in our series. So this is a continuation of the second video that we did a while back. Please go through it if you haven't, and also the first video, which actually the start of our series. Yeah, this is a continuation where we'll be speaking a lot in depth on the pattern recognition and how it is connected to AGI. So moving on. Yeah, so the first question we kind of get asked when you are talking about deep learning or anything is how deep learning understands the features. So that's where the representational learning comes in. It is like learning the features and learning the right set of features. It's not like learning anything. So, and this architecture that you are seeing, that any architecture you take, it's kind of a derivation of the Hubel and Wiesel experiment which they did a while back. There's a good video on that in YouTube. So as you can see, this is how our vision system is there. So the mammalian vision is based on a hierarchical structure, and our network is all about that. It's kind of based on hierarchy. We have input, we have hidden layers, and then we have the output. Now, this architecture is all about understanding the features and reproducing the same thing at output. Now, when we talk about pre-trained model, there's a lot of buzzwords that we kind of use pre-trained models to get the weights and biases to start our modeling. That's the initialization we use sometimes to train our model. And then we do some kind of transfer learning, one-shot learning, and on the data set to get what we need. Transformers are a big deal right now. There are BART, GPT, and all high-end, and there are various variations of that has come, which is doing a very good thing in the NLP domain, language domain. Now, when you talk about deep learning and anything, what we want is a generalization. Now, that is what we really want, generalization. Now, generalization is something where the model is doing well in a test data set compared to a trained data set, which we normally want. Now, what happens is, like, in reality, this is not always the case. Like, when we talk about the generalization, it means that our model should be better at predicting using the unknown set of data sets, which we want. Like, we want our model, when we deploy our model in production, there will be lots of data which the model hasn't seen that will come in, and the model should infer from that. We will be using that model to predict, to infer, to take business justification, to do business decisioning and all. But sometimes what happens, it doesn't the case always. We have to train, retrain, probably over weeks, months to get a decent amount of model. Now, your model is good when you say that you have a good accuracy in your trained data set. Yes, say 98% accuracy is very good. And we also make sure that your model does not overfit. I'll come to that later. Now, if your model does not do well in the test data set, then that model really is not giving that amount of impact. Now, moving on. Now, all generalization does, we talk about overfitting, like, and now overfitting is a very big error we get while we talk about generalization, how to train the model. Now, what overfitting is necessarily is basically your model is understanding your trained data set so well that it is not able to reproduce the same kind of output in an unknown data set, which we call the trained data edge data set or validation data set. Now, this is a problem. We don't want our model to learn everything, every single thing in the data set, and then it is not able to do good when it sees unknown data. Now, that's where the balancing comes in. I'll come to that. There is a good picture of that. But what the crux of the matter is, we want our model to do well in that test data set compared to trained data set. Now, moving on. This is a very good paper. Please go through it. Understand deep learning requires rethinking generation. What the authors here have done is, like, they have done a series of experiments to make us understand, like, why generalization is important, and why, when you talk about deep learning, any high-end models, generalization is one thing that is required right now. Now, deep neural networks usually feed random labels. When you train the model, you will see that your model is better at understanding so many things. Like randomly, it will it will understand all the labels and all everything. Now, while reproducing, if your model does reproduce good, then it's good. If not, then that's what the problem. It has learned things in the trained data set which it should not learn. That's when all the hyperparameter tuning and other stuff comes in. Now, explicit regularization. Regularization is one technique which we very commonly use to reduce generalization error, which means that, as I said, like your model does well in test data set, does not do well in test data set, but trained data set. So regularization, we can prevent that overfitting and all everything, and there are other methods as well. But let's talk about regularization. Like use regularization when your model is overfitting. Now, moving on. Yeah. So these three questions, like what it is that distinguishes a network that generalizes well with those that don't, like what it is that is. So you get a good model, very good model. It is generalizing perfectly. You also have a model which is not doing well. Now, what distinguishes that? It mainly because you have some tweaked the architecture, the good architectural design, or you had led to you make your model more interpretable in the sense that you tweaked your model, you know where you are tweaking. That means you will be able to explain why your model gave that a good result. That is very important thing. When you are explaining your model well, that means you understand how the model has done all the steps in between to give you the output that it gave. Now, it means explainability as well as it means that it has the model architecture you have fine-tuned very well. Now, this can mean the difference between a model that does well versus a model that does not do well. Now, but generalized well, we mean that network performs well on a trained data set as well as perform well in test data set. Meaning, you cannot take a model that produces 60% accuracy. No, you cannot. You want our model to be as much accurate as possible, because sometimes the business decision, like many critical things, are dependent on model producing the right set of output. The right set of predictions. Now, we want our model to do well on trained data set. Yes, that means that I have trained my model good enough to take a call. Like when I can actually freeze my model. Freeze my model means like I can tell that, okay, my model is now 98%. I'll stop there. Okay, that's good enough to proceed with the next steps. Next steps is you train your model in test data set, validation data set. Then only after that only you can finalize your model. Now, we want our model to do well both in the trained data set so that we can take the call, and as well as in a test or validation data set so that we can take the call that, okay, my model is doing well in your test data set. That means it is ready to be deployed. That means my model is good enough to predict when it sees the unknown data sets. Now, generalization means difference between the train error and test error, and it should be greater than. The train error, it's your model does well when the test accuracy is greater than train accuracy, which we want. But when we don't get that, what happens? We do various iterations and training and retraining to get that. Moving on. Now, why we lack current generalization? Limited transfer learning. Yes, there are so many pre-trained models available. You go to TensorFlow website, you will see lots of pre-trained model available. You can take any of them based on your the problem you are solving. You use them, you take their weights and biases, and you use them to initialize as a start for your model training, and then you can proceed. But it is limited. You cannot use all models, every model for your and for your analysis. Like, so for example, model trained on, say for example, understanding languages, you cannot use them to classify, say for example, cats and dogs. It is not going to do well. That's the limited transfer learning we have. But within also the same thing, like a model trained well to understand a tables and chairs versus a model trained good enough with cats and dogs. But if it has not seen that, it will probably wrong. It will not be able to do well in that. So there's a limited transfer learning available. Now, as I said, overfitting is a very common issue which we normally see. Overfitting and underfitting, but overfitting mostly we see our model does so well in your data set that it fails to do well in the test data set. Now moving on. Yeah, so this is the picture I was talking about. Now this is the three things when you train a model. A, it can underfit. B, it can be optimum, which is what we want. And C, it can overfit. Overfitting means low train error and high test error. A low train error in the sense that your model is almost perfect. And high training error.
While training, when you are basically when we are thinking, right?
Yes, yeah,
While
that's right.
With the training data.
With the training data, if it is, if you get 99.99999% accuracy, that means your model has understood your training data very well, which means that it is not a perfect world, which means if you get a accuracy closer to 100%, meaning that if somewhere or the other it is and something wrong. It has learned the noise, it has learned everything, it has overfit. So that's what we don't want. And your model can do the opposite as well. It can underfit. I mean, it is not able to understand anything. It is giving 50% accuracy, 60% accuracy. That means your model is not able to do well in your training data set, meaning you might have to change the architecture or might have to think of introducing some other model.
I agree.
Yes. And what we want is the optimum, which is the low training error, low test error. This is the place where we want. This is the crux of the matter. I mean, this is what we want, but we don't normally get that because of the fact that underfit and overfit. We normally think of that, like when we train a model, we either go underfitting, we either go overfitting, we go to the extreme end. But in the optimum part, it takes like months of training. Sometimes it takes months to train your model to get a decent level accuracy. So moving on. Yeah, as you can see, there are three things: the new learning concept, how a model learns. So there has been some research done where there's something called knowledge graph, there's something called art, there's something called human in the loop. I'll come to that one by one. What is knowledge graph? It's basically, if you check Facebook, is a best example of knowledge graph. You take yourself, you are friends with, say, 100 people. Those 100 people are friends with 1,000 people more, like mutual friends, friends of friends. Those relationships are there, right? In Facebook, it seems.
Sure.
So those are like the graph. If you plot them, you'll see a graph. Like you take yourself, then all the nodes are you, I mean, all the people, and all the edges are the relationship. It can be friends, it can be friends of friends, it can be relative, it can be sister, brother, sister, anyone. So this, if you plot it, you'll get a relationship, you'll get a graph structure. Now that is knowledge graph. With knowledge graph, it is good because we can understand the intricacies of the data. We understand, I mean, how the insights we draw from the data. Okay.
Right.
Yeah. So art is adaptive resonance theory. Now, adaptive resonance theory is a type of neural network where it is, I mean, this theory was proposed by Grossberg and Carpenter in 1987. The art uses unsupervised learning technique. The term adaptive means it can adapt to new learning, and resonance means it will not going to delete what it has learned previously. Now, this is very important concept. This is how we learn. Now, when we learn something new, it doesn't necessarily mean we have deleted everything from our brain, what we learned previously. What we do is we keep on appending. Okay. Now, this is how we learn. This is a new concept. Now, new learning will happen when your model has seen, I mean, it is training well, it is adapting to new data, so it keeps on adding and all. But it should add, but it should not be overwriting or deleting anything it has learned previously. Now, human in the loop concept is very good. It is like you are using the machine as well as the hybrid, I mean, human machine hybrid, you can say. Like there is a machine system, but in between somewhere there is a human touch where the human is inputting his or her own inference there, and the machine is giving the output based on what it is supposed to do. It's basically machine and human working in tandem, working together to give the inference. This is a very important concept. It's a hybrid concept. I mean, it's a hybrid thing, which is the new thing. You can learn more about it. So moving on. Yes.
Right. Now, so thanks, Tamal. And So before I kind of take a deep dive with this idea, we have seen like very recent examples of Gato. Mu0 was there for a couple of years, and this idea has come across. And I think so. What do you think about what is your commentary, or like what have you like taken out from Gato? Like, because there is a lot of buzz around that. So what do you think about?
Yes. Yeah, there is a lot of buzz around Ghetto by DeepMind, and now they are claiming that this. I mean, the bold claim is that we are nearing AGI. I don't believe that yet. I don't believe that yet. But given Ghetto has learned from 600 different tasks, which means that it is getting there what we want, like the generation, like an agent which can perform well in multi set of environments, like as Ghetto is doing.
Yeah.
Now it's a positive step in the right direction, I will say, but I think it has long way to go still, and we'll see in the coming years how it is doing. Doing well. Let's see. We'll see.
Yeah,
definitely. Yeah. For the part that I am very kind of hopeful that this is where we start solving the key challenges of AGI, what we have currently.
Yeah, so I have read the paper and I found it interesting that it was able to generalize over so many tasks. But still, there is few things missing, and I still see that it is like a very reactive system, like what it is seeing and it is kind of doing on that. And definitely data intensive. So I'm not 100% sure, but it does look like, yeah, there is a very good common framework now available in a form of reinforcement learning, or like in a hybrid model. There's definitely a hybrid model which is able to solve this problem. And it does showcase the power of generalization done right, even while using, when you are using deep learning with alongside with reinforcement learning itself. And this is definitely very extremely impressive. And I was impressed with this paper and the results that they were able to get. Hey, so fundamentally what I was saying is, and it took some time to restart everything, but idea of generalization has been there for quite some time, and no AI model or true AI model will ever be complete without this idea of generalization. So Gato seems to be a good step in this direction, but fundamentally where we are trying to go and we are trying to look is, and of course, based on this, people have started talking about something called foundation models. And last year in August 2021, there was a discussion around foundation models at Stanford. And people were talking about creating a model. And I think Facebook has recently launched something called data to it. So they are kind of claiming that any kind of data you throw at them, like image, audio signals, or even text data, it will be able to, a common framework will be able to convert them to a vector or vectorized representation. Foundation models' fundamental idea is that you have these models which have been trained on broad set of data at a large scale. Now, usually using self-supervision, because if it has to be completely supervised, that also is not going to work very well for us. So when we say self-supervision, the model needs to regulate itself. Okay, you can define it like something, think like a policy gradient at the end of the day, reinforcement learning. So once you have that, you are able to kind of see or kind of build up this system, which can be adopted, fine-tuned, or you can use in context learning to a wide range of downstream tasks and applications. So let me give an example here. Tamal has been able to find a really good picture here, and this kind of represents the idea of foundation model. Okay, that you have different kind of data. You have text, you have images, and you have speech, structure data, various kind of sensor signals, 3D signals. They all are put or calendar passed through foundation model, and foundation model is able to utilize them all. And thus these can be adapted to different minor use cases or some global use cases as well. So you can have information extraction, image captioning, object recognition, DALL-E 2, like recently that has taken the world by kind of like a surprise. And the idea is that like we write a good caption, one line or something, and we are able to find really good representations and like pictures which are just mind-boggling if you have seen. So I think me and Tamal were exploring DALL-E, and we were looking into their Instagram page and like what other people have posted using their APIs. Right now it is a paid API, but if you get into the wait list, you can at least try to experiment. And you will need some kind of a foundation model. Okay, now there have been debates that how effective it is. And again, another example here, which is pretty good according to me, is like this can be utilized, let's say in pedagogy. Okay, while teaching itself, we can think about building this kind of system where We have various teaching materials, which could be textbooks, these could be recorded lectures, curriculum, exams, and assignments and whatnot. And then you merge them with subject matters. Okay, you have maths, physics, chemistry, social studies, history, language, drawing, anything creative over there as well. And think that can there be a set of common model only, and where all the data can be pushed through and all can be adapted and interpreted for understanding, learning, providing personalized, providing like kind of personalized learning for every student, and how teaching methods are helping us, and even understanding subject matter. So this can be utilized in so many fields, and this brings down the cost of AI models training and putting them in production, because so far for each of these tasks, we will have to put multiple models in parallel, and they all have to be trained separately. And any data shift that will happen, and that is almost bound to happen in future, we'll have to keep retraining them in parallel. And again, I'm going to talk about lifelong learning. So this needs to evolve. But foundation model is somewhere that we need to look at how can we take multimodal inputs and pass them through the same model, and they will be able to kind of vectorize them, and then they can, if commonly a common model can vectorize and convert them into proper numeric representation, we should not have much problems then utilizing on kind of tinkering with that and converting it. So what I'm really trying to say is, cat as an animal, when it is given a visual stimulus to you, okay, like it's shown a picture of cat. When you say the word cat, audio, and then when you write CAT, right, cat, can all three primarily get very similar representation? Because when you think about it, whenever I show you a picture of cat, I say the word cat, audio, or you see the word CAT written somewhere, in our own design of our own mental model, it kind of points to the same place. See, machines right now have not been able to successfully do that. You will have to train separately. Cat for visual, like using CNNs or something, we can get visual representation and features. That's all right. But see, when I say the audio cat, okay, or see the word CAT written, our brain makes these quick associations very easily. And for all three, our brain will get similar representation, which can be a mix of details about cat, how the cat looks like, what are the properties of cats, right? How it is used in any text, okay. So all of that comes together, and that is something that we want to utilize with multimodal data sources, and that would be requirement, as a serious requirement to merge data inputs from various sources and still get the same outcome. And so why is they are called foundation models? Okay, so existing terms like large models, pre-trained and self-supervised models focus only on the technical dimensions, but very much fail to highlight the paradigm shift in accessibility beyond world of machine learning experts. And we want to make AI possible or like available to everyone. That's the whole point. So thus people also experimented and said general purpose model and multi-purpose model. But I think the foundation model has captured the true meaning, what we really want to do to identify this emerging pattern. It is like the big foundation, like it is the common foundation on which a building is built. And if the foundation is not good or strong or robust enough, you will not be able to build a tall building. And similarly, we can think here that if the foundation model is not going the right direction, then we will have the same problem. Okay. Okay, and now foundation model itself is incomplete, but serves as a common basis. Understand, I'm not saying foundation model has solved everything or would solve everything. It is just the basic, it's just the base that we have to create, that all of this data, multimodal data, does not have to be passed through separate models to be interpreted. And you don't have to come up with different parallel models, even while in deployment or production, but rather you can have a singular foundation model. And then it can be modeled, or that vector representation can be definitely sent to different task-specific models. Okay, and we can adopt this. That's the whole point. Okay, and understand, if it is poorly constructed, it is a recipe for disaster, and you will have to have a very well executed and a robust implementation so that it becomes a bedrock on which everything else is built. And I will ask people to look into data to vec released by Facebook a few months back, and that is like, I think, a step in this direction, and other companies also have, other research groups have started to look into this as well. Okay, now right now, of course, I cannot guarantee foundation model. It's a very, very new talk that has started to happen in the AI world, and people have started seriously thinking about it. But let's see if they do become the trustworthy tool that we want them to be. This is a good one Tamala has been able to find. So this is like an image generated by one of the foundation models idea for prompt of like AI model. And it does looks like a kind of a massive connectome with a lot of connectivities, very similar to what your neurons would be. Generated by a machine, generated by algorithm, and looks extremely interesting. And we can see these connectivities, which according to me is again very similar to what we are so used to seeing at the end of the day with our brain itself. Okay, so this will be definitely interesting. Now, but even if you have foundation models, that's all well and good, but that only converts the data into numerical fashion. Okay. How do you learn new things? Okay, that's something that we have to teach machines really well. Not just that you start with a model and then you kind of start and kind of just stick with that model. So in a modern day scenario, I will say any machine learning or deep learning system kind of learns in isolation right now. What does that means is it is like hidden from every other data because right now there's no foundation model so far, which can serve as a continual basis, and there's no lifelong learning so far that has been developed correctly. So without the lifelong learning capability, AI system will probably never be intelligent. That's the whole point, that even if you make a very powerful system right now, but there would always be more tasks or variations of tasks which are going to serve as some kind of barricades. And then again, you will not be able to do better over there. And again, your intelligence kind of gets stuck. So of course, the way humans do, okay, fine, we try new things and we usually do really bad at them initially. But we practice, we keep becoming better over there. And that is what exactly we want to make sure that machines or AI algorithms are able to do it very much on their own. This should be like their nature now. They should not have to manually retrain them again and again. And our world is practically ever changing. And as you understand, it's a non-stationary environment. So this is like a form of active learning. So this is something that we have to look into it very seriously, as a matter of fact. Now, if you start to find lifelong learning or continual learning, okay, you or active learning, you will find most of the research is barely 5-7 years old. There have been ideas. It's not that people have not these ideas for long, but most of the research papers, me and Tamal, whatever we looked, even in the books that we looked, were recent, fairly recent. And that gives us an idea that is still a very active area of research. And there's no one clear-cut winner. Although I will be talking about one architecture which I personally liked, and that is available in the book called Lifelong Learning. We will put the links over there. So you can definitely look into that. Okay. How would you define lifelong learning? So at any given time, the system has learned to perform n tasks, some given n tasks, like cooking your food, washing your clothes, okay, cleaning your homes. But there could be more tasks, right? Maybe I would have to ship this agent or actual physical robot to supermarket to buy some groceries for me. Okay, that would be n+1 task. Okay, so so what we want to see is, or what we want to develop the intuition as, that whatever knowledge you have gained from past n tasks, we should be able to help learn n+1 task as well. So what would be the characteristics of such system if we have to really think about it? It has to learn continuously, definitely. And in ideally an open world with all kinds of different inputs. Okay, so foundation model kind of also becomes extremely relevant, that because you will have to deal with different inputs, it's better to have a foundation model that can deal with different sets of inputs and accumulating the previously learned knowledge to become more and more knowledgeable. So of course, keep accumulating this knowledge through knowledge base. And I would want to talk about knowledge base in our next video, because I do think that's extremely important. And then using this knowledge to learn more knowledge and adapt to problem solving. And this is what we humans are really good at. So even when we deal with some new domain, we kind of use our existing knowledge to acquire more knowledge. And it is kind of this, like, how do I say, like kind of a cumulative growth, if you have to say, okay, like it's compounding interest, like you can understand, like the way compounding grows, something very similar to happens to knowledge as well. As your knowledge grows, a lot of these ideas start to compound, and actually learning new knowledge becomes extremely easy for you, or the speed or the time definitely reduces in learning new knowledge, and definitely adapting it becomes a little easier for us. And we want to discover new tasks, new problems that has to be learned, and then learn them incrementally, step by step. We can keep learning them. And of course, it has to be done live. So learning on the job or learning while working. Very similar to what human brain does. We don't have like two brains, which one is meant for learning, one is for execution. Although one can talk about system 1 and system 2, but I think they differ in the way they behave against a given problem statement. Right now, I'm just talking about here, the model which is put in production usually, that itself doesn't changes. You are taking a parallel model or you have a copy of that model and you are retraining that model with the new data so that you can accommodate for the data shift that has happened. But we want to make sure that same model keeps on working and keeps developing or keeps making itself better. And that is what our overall aim is. Now, this picture is, I think, one of the good representations I was able to find in lifelong learning. And there are a lot of elements here, and you can see there are task managers, application model is there, and then knowledge-based learner, knowledge base, as well as task-based knowledge manager. If you don't mind, I will just point it out. So this task manager is something where you are containing this directory or you are maintaining all the previously learned tasks. Now, task itself could be of two types. Okay, like one could be like a task could be completely related to something existing already. Okay, something that you have already seen or something you have already built. There would be a very minor various, a very minor like difference, if I have to say that, a very minor difference that will be actually there. So in that case, we are not really excited about that kind of task. Okay, but the problem one is which changes abruptly. Let's say there is a cooking robot that only knows how to cook. But you all of a sudden say, you know what, now you have to start going to office and maybe start maintaining payroll. Immediately, it will not work like that. Okay, but still, we want to build a system which can do this. Then we have this idea of knowledge-based learner. This is knowledge-based learner plus knowledge base is really important. Okay, because these things will ensure that knowledge is retained and then it is utilized. Now with the application, we can maintain knowledge in results. So whatever results we get, that is also updated. So whatever you did with application, so model will run and application would be executed. And that will give us feedback, like what happened, what did we learn, what mistakes we made, right? Okay, and then a task-based knowledge miner is there, which can keep expanding or keep looking into different tasks. And based on those tasks, it can continue to mine new knowledge. It is like, I know I have to do a project on, let's say, some biology. Okay, let's say biology, I have to do some project. Let's say I'm not a biology student, but I can start looking well in advance in different ways. So let's say we have to publish new videos on some topics. Let's say we do not know much. Okay, we will have to start looking well in parallel about those topics as well. So that will be something that will be required. Okay. And there are like a lot of components, and I would really urge everyone to read the book because that definitely is far better. But still, I would like to kind of give you my own 2 cents here. Okay. So knowledge base is like which stores previously learned knowledge. Okay. So past information is stored, stores information from past learning. Okay. Models, patterns, or other forms of results. Then you have meta knowledge miner. It implements super knowledge mining in the PIS, and it maintains a knowledge archive. And there is you have a knowledge store, okay, where it stores mine knowledge and integrates from PIS and well as the meta knowledge, MKS as well, okay. And knowledge reasoner, there has to be inference. At the end of the day, we have to build an inference which can use a knowledge-based inference and in MKB, that is meta knowledge, meta knowledge based learner, okay, and integrating it with past information, okay, past information store to create more knowledge. And this is like a very important concept. Like you need to interpret like whatever the data that has just come or whatever inference that has just come, how it will be utilized to create more knowledge, okay. And then knowledge-based learners are there. So this department needs to be able to use knowledge before learning, okay. So this is like a knowledge-based learning, making users learn knowledge to perform new tasks. So you have some knowledge, and based on that itself, you are performing new tasks. Right now, we are not talking about any particular learning after doing the task. And then you have task-based knowledge miners. It will keep, this module is particularly there to extract knowledge from specific knowledge base for new tasks. So as I told you, if I have to read or do some work in biology, and let's say I do not have, but we can either build this knowledge base, or again, for me, like knowledge base would be Google and Wikipedia, right? Google will help me with the search, and Wikipedia might already contain a lot of this knowledge. So this becomes really, really important for us. Okay. And of course, as I said, a learned model is your predictive layered models, deep learning models, a hybrid model, whatever you want to think. Application is the practical application, whatever you are applying. So when you apply, so when you make a prediction for, let's say, in a salary prediction, you want to do a face detection, object detections, and whatnot. So this application can also provide feedback for knowledge-based learning. So it can tell you that, okay, what went right, what went wrong. And this feedback, something very similar to in reinforcement learning, could really be helpful for us. And we have our task managers. We receive and manage incoming tasks. So we know what tasks we have to see. And this can handle the task conversion and present even new tasks for the knowledge-based learning. Okay. Now, why you want to do this? So, Tamal, I think I would also like to know your thoughts here.
Yes.
According to you, why lifelong learning would be advantageous for us?
I think this is one of the key things which have come up over the past few years. Lifelong learning, adaptive resonance theory. I have seen a relationship between ART and lifelong learning. If you see the definition of ART and also definition, few of the characteristics of lifelong learning, they are quite similar, which means that there is some relationship between the way those algorithms work and our brain kinds of work in the same thing. Like, as I said, like we don't normally delete or overwrite anything which we have learned over the years when we try learning something new. But what happens is inside the brain is that it gets appended. I mean, your knowledge, we say that you go, learn new things and grow. We often give this kind of advice to in office, in corporates. I mean, you grow by learning new things. Why they say that? Because when you are exposed to new things, you get experience. With that experience you are gaining, you try to implement those experience in either your current task or some of the tasks which you are planning to do. Now, this is how things happen. This is how we evolve. Like, this is how humans have evolved over the course of millions, 100,000 years. Like, they start learning things and they start implementing things. Now, an agent, an AGI agent, which you are, which will be a reality in sometime in the future, we want our agent to do the same thing. We will expose the agent to certain degree of knowledge which we already have, and then the agent will try learning and learning. Example, very good example is the Go, AlphaGo.
Yeah,
like it has defeated world champion in Go like 2 or 3 times. Now,
I think it
how
was
he has done
four
that?
out of 5 times it defeated actually.
4 out of
correct.
Yeah. 4 out of 5 times, which means that it has learned from its mistakes. I mean, it is keep playing against itself, as I read in their blogs, like it kept playing against itself, trying various scenarios and all these things, and it has learned how to beat that guy. So this is how it is. It should be a combination of art, it should be a combination of lifelong learning, it should be a combination of all these things. If we want to visualize an AGI agent, this thing has to be there. This is how we learn, and this is how we want our agent also to learn. Yeah, I think this is an important step towards AGI.
Definitely. And again, I think I was mentioning some advantages already. You will ideally would not have to explicitly retrain the learning model with updated data in isolation. This model, this kind of learning mechanism would keep on learning as the data changes all by itself. It is very much in the design. The performance continues to improve even at the frontier of data compute as well as the model scale. So even if the data and the model scales at a terabytes, exabytes, or petabytes levels, it would be able to work over there. And again, such models reduce a lot of redesigning, and this is like a major cost right now to a lot of corporates, that even if you have one model, sometimes it becomes useless after 6 months. Okay, and you again have to redesign or recalculate everything and retrain, refine tune everything. Again, has to be done everything. That redesigning part of learning models, and moreover, we will be able to ensure this kind of system is able to adapt in future with data drift and concept drift. That's very important actually. This could help us kind of bringing an end-to-end solution from start, from the wherever you have a requirement analysis till where you have deployed for lifelong learning. That would kind of give you end-to-end system design, which would be updating itself to different tasks, and of course look like an intelligent entity similar to human beings. Like, I will not still say it is complete agent, but it's a very important step we have today. And this could reduce the cost of adoption. This is something that's plaguing the industry right now, that yes, we have so many good models. Like, you can have good models around NLP, like language models, audio signals, like these days, even you can see that audio conversion has become really good actually. And plus visual tasks, we are already doing a pretty state of the art. It is even better than what humans have been able to do. Even through reinforcement learning, one can see through AlphaGo, or like you can just use Mu0 as a good example, which has been able to play different games without explicitly being told the rules over there. I know those are highly deterministic moves, but still, it has been able to do that. So, but the problem is any of these models is so narrow. You cannot just take one model and just put it in the other domain and it will start working. It just does not. There's a lot of engineering effort that goes around to make it workable. This could help us reduce the cost of adoption in AI with different domains with minimal overhead. And that is where we are aiming. Okay. And as I think Tamal already has said, and I would say that in search of AGI, we need to ensure that our learning algorithms needs to continuously evolve. Jan LeCun actually very recently mentioned this point in one of Facebook or Twitter posts. I'm forgetting where it was. I saw. By the time human child turns 5, she has seen the equivalent of 800 million images or frames, if you have to understand. Instances, images, frame, whatever you want to understand. 800 million while you are not sleeping, let's say. So whenever you see these frames, you have multi-modal inputs, you have video, audio, and touch usually for a human baby. To learn how the world works through via continuous lifelong learning approach. And most of it is in very self-supervised learning. Not everything has to be taught to a kid. So let's say they touch a hot surface, they feel the burn, okay, and they pull that. So this gives them a feedback very similar to reinforcement learning, right? This is like a penalty. It's not, or like you can call it a negative reward if you wanted to call it. Okay, and if they like something, let's say they eat chocolate and they really like the taste, they want to eat more chocolate. Okay, so that happens a lot. So we need to envision an end-to-end design about building such lifelong learning or continual learning or active learning scenario, which provisions for data collection, lifelong learning, machine learning, and improvisation in case of data shift or concept shift, and of course be able to accommodate newer concepts. Okay, accommodate newer concepts without having some forgetting or catastrophic forgetting of the old concept, which is a very big problem right now. If you start teaching it about new classes, many times it starts underperforming in the existing classes. So again, data has to be mixed, reshuffled, and retrained. But didn't we already train it on 10 million images? How can it forget that? But that's what happened. That's what so far happened. And that is a big problem that we need to solve. And again, we are doing the research. People are really getting, large companies like Google, DeepMind, Microsoft, Facebook, all of them are working, and even a lot of universities and active researchers are looking into this. And this is something that I hope as a community we are able to solve it in next 3 to 5 years, because this will really put a dent in this quest of AGI and the challenges around AGI. One major challenge will go away if we solve the problem of foundation model and lifelong learning. If both can be combined, you will have a really powerful system, and the cost of adoption in various companies, corporates would actually come down. So I think, Tamal, this has been a very good experience, and I know it has taken a lot of time to build this video, but I think this discussion was due, especially after pattern recognition, because yes, we understand pattern recognition at most times when you learn machine learning, you have to know pattern recognition, or if you're from computer science, exactly, you have to know all this, right?
Yeah, and to add to what you just said regarding cost of adoption, I did say a few slides back that the limited transfer learning. Now, because of that limited transfer learning, the cost of adoption of any AI frameworks or anything, it increases because of that limitation. Now, if we solve lifelong learning, very well, like we know how the adoption will happen, how the model will run from itself. So if we do that, this limited transfer learning and the cost of adoption will reduce drastically, and then we can have a seamless system which can do practically anything. That's like the step forward what the Gato model has taken. Like it has solved those things. Trying to solve. I'm not saying 100% solved. It has solved few of the things, at least 600 tasks. But it's a step towards that direction. So I'll say that we need to build on lifelong learning as we go forward towards AGI.
Yeah. Thanks, Tamal. Thanks for your thoughts, and
Sure.
thank all of you actually. And that's all for this video. One next topic that I'm really interested in is in building the right knowledge base for AGI, because we showed you will require knowledge base to store these knowledges around whatever has happened and what will happen for the next task. This is something we are going to discuss very soon, and we will try to bring out this next video as soon as possible. And thank all of you, and thank you, Tamal, and we will see you
Thank you.
really soon. Okay. Bye, guys.
Sure.
Bye.
Bye, guys. Bye, everyone. Thank you.
Okay.
Perfect.